So you think the world around you is made of solid stuff, right? Particles, little bits of matter. Well, what if I told you it's not? Today, we're diving into the one experiment that completely shattered that idea and proved that our reality is fundamentally made of waves. Let's start with a really wild question. What if a particle, say an electron, was also a wave? Now, I know that sounds like something out of science fiction, but back in the 1920s, this was a radical scientific idea that kicked off one of the greatest detective stories in all of physics. So yeah, it all started with a ripple in our very understanding of reality. Okay, so you've got this brilliant physicist, Louis de Broglie, back in 1924, and he has this beautiful idea. He's thinking, look, we already know that light, which we thought was a wave, can sometimes act like a particle. So what if nature is symmetric? What if particles, like tiny electrons, could sometimes act like waves? Now, this wasn't just some philosophical musing. He actually backed it up with math. But you know how it is in science. An elegant hypothesis is great, but you need hard proof. So how in the world do you even test an idea this strange? How could two physicists, Clinton Davison and Lester Germer, figure out if an electron was a tiny little bullet or a wave spreading through space? Well, here's the setup they built. You've got an electron gun. Yep, it just fires a beam of electrons. The target is a piece of super pure nickel crystal. And then you've got this detector that can swing all around to count how many electrons scatter off at different angles. And the whole shebang has to be in a high vacuum, because you can't have your electrons bumping into air molecules. Think of it as a game of microscopic target practice. And this is where things get really, really weird. Because what they expected to see, based on everything physics knew at the time, and what they actually saw, well, they weren't even in the same ballpark. Think about it. If an electron is just a tiny billiard ball, it should just bounce off the atoms in the crystal pretty much randomly. You'd expect to find scattered electrons smoothly, all over the place. But that is not what happened. Instead, they found this bizarre, intense spike of electrons at one very specific angle. The whole billiard ball model, it was dead in the water. And this chart just says it all, doesn't it? The classical prediction is that gentle slope, a smooth, kind of boring fall-off. But the reality? Whoa. That is a sharp, dramatic mountain rising up from a flat plain. Something way more profound was happening here. And get this, the numbers were incredibly precise. When they set the accelerating voltage to exactly 54 volts, bam, that peak appeared at a sharp 50 degrees. This wasn't just random noise. This was a signal, a clue. The big question was, what was causing it? It turns out the answer wasn't just in the electron itself. The secret was hidden inside the crystal. You see, the nickel crystal wasn't just a random chunk of metal. Its atoms were arranged in these perfect, orderly, repeating layers. And that perfect structure acted as a natural diffraction grating. It's like when ocean waves pass through the narrow gaps in a harbor wall. They bend and spread out. That phenomenon is called diffraction. And the crystal was doing that exact same thing to the electron waves. So now you have all these little electron wavelets scattering off the layers of atoms. And what do waves do when they meet up? They interfere. Now, at most angles, it's a total mess. Wave crests mute wave troughs, and they just cancel each other out. That's destructive interference. But at that one magic angle, that 50 degrees, all the scattered wave crests arrive perfectly in sync. They add up, reinforce each other, and create one giant wave. That's constructive interference. And that's your intense peak. And this is where it all just clicks into place beautifully. Remember de Broglie's equation? It connects an electron's momentum to its wavelength. And here's the absolute kicker. You can change an electron's momentum just by changing the voltage that accelerates it. So Davison and Germer realized they could literally tune the wavelength of their electrons just by turning a knob. How amazing is that? And Bragg's law provided the final piece of the puzzle. This law perfectly predicts the exact angle where you'll get constructive interference based on the wavelength and the known spacing of the atoms in the nickel crystal. So they plugged in the numbers, the wavelength from de Broglie's equation and the atomic spacing for nickel, and the theory predicted the peak should be exactly where they saw it. The math matched the experiment perfectly. The mystery was solved. But hold on, because there's this fantastic human twist to the story. This groundbreaking discovery, you see, almost didn't happen at all. So originally, their nickel target was what's called polycrystalline, basically a jumbled mess of tiny crystals pointing every which way. Then one day, a vacuum flask in the lab cracks. Air rushes in, oxidizes their hot nickel target, and ruins it. So to clean it, they had to heat it up. A lot. And in doing so, they unknowingly annealed the metal, which caused all those tiny jumbled crystals to merge into large, perfectly ordered single crystal regions. That ordered structure was the whole key. Without that lucky accident, they never would have seen the sharp diffraction pattern.
So, you see, this discovery wasn't just about confirming a theory. It literally handed humanity a brand new set of eyes to see the world.
The principle that matter is a wave led directly to incredible technologies. We use it in something called LEAD to map the atomic structure of surfaces. It's the foundation for huge fields like surface science. And, of course, it's the direct ancestor of the electron microscope, which lets us see individual atoms. And maybe the most profound part? This isn't just about electrons. It applies to all matter. Protons, neutrons, even you and me. We all have a wavelength. And let me be perfectly clear. Matter waves are not a metaphor. They are not some philosophical idea. They are a physically measurable reality. This experiment was the first solid experimental proof that our universe runs on the strange and wonderful rules of quantum mechanics. And that leaves us with a final thought. The power of a microscope is limited by the wavelength you use to see. By mastering the wave nature of matter, we can make an electron's wavelength thousands of times shorter than visible light. So, what new worlds does that allow us to see? We didn't just discover a new law of physics, we built a new window onto reality itself.